Previously, by using the translating frame, we obtained the relative displacement, velocity, and relative acceleration by differentiate it directly. So you have a relative displacement v measured with respect to a given by xi, yi, and zi here. For translating frame, the unit vector ijk do not change with time. Therefore, if you differentiate I with respect to t, differentiate j with respect to t, or differentiate k with respect to t, since the direction is constant, therefore you will obtain 0 for this derivative. So for the translating frame, you obtain the derivative for the direction equal to 0. In this case, we take the derivative of the magnitude in order to find the relative velocity. In this study, we use the capital X, Y for the observer O here. This indicates the fixed reference frame or inertial frame. And we use the small letter X, Y, Z for translating frame. And you have X, Y, and after rotate you have X prime, Y prime. So this is for rotating frame. If you measure the motion with respect to A, and A is the rotating frame with the omega, you need to be careful. We use the symbol omega here. For object angular velocity, the next omega symbol is for the angular velocity for a rotating frame. For a particular moment, the frame is at xy coordinate. In next moment, the frame rotates to x prime and y prime coordinate. And you see there is a change in terms of the unit vector I direction. I become I prime, and your j direction is also changed to j prime. Therefore, for the rotating frame, the direction will change. And in this case, di over dt, dj over dt, dk over dt might not equal to 0. Therefore, we can now calculate the relative velocity by using this calculation. We need to consider the change in terms of the direction. In this figure, you have a particle travel in circular path, and the A is the rotating frame. The frame is rotated with angular velocity and angular acceleration with respect to the fixed frame. If the angular velocity vector is given by omega k, so you have x, y, and z axis. So you should know that we use the omega symbol here for frame and omega symbol here for the object. To avoid confusion between these symbols, we will call this symbol as ohm, and we will call this symbol as omega. It can be also called as omega uppercase for this symbol and omega lowercase for this symbol. So you have ohm in k direction, therefore you have the angular velocity here in the k direction. By using the right hand rule, you must know that this angular velocity is rotated in counterclockwise. And therefore you have di, which is the change of the I direction in here, and you have dj, which is the change of j direction in here. Previously, we measured the velocity of A with respect to B, and also we measured the acceleration of A with respect to B. So in this case, we call the B as the translating frame. This is because B is moving with a linear motion. In the next moment, B will move to this point, and you see the frame is translating. In this case, we want to measure the velocity and acceleration at B with respect to A. A is called the rotating frame. This is because at the next moment, A will move to this point, and you see the frame. A is called the rotating frame. This is because when A moves to the next point here, you see the frame is rotate. Let's set the coordinate for O, A, and B here. So we know O is fixed, therefore you have a fixed reference frame, which is capital X and capital Y. So since A is rotate, therefore you have a rotating frame with small letter x and y. And then we want to measure the velocity at B here. with respect to the rotating frame A, and also find the acceleration B with respect to A. So your velocity B is moving to the left. Based on our coordinate here, move to the left is negative. So this is in I direction. So you have negative 8I for your VB. And your acceleration at B here is deceleration. Therefore, it must be opposite direction to the movement. Moving to the right hand side is I direction. Therefore, you have positive 5I for your acceleration at point B. The velocity at point A is always tangent to the path. This is called the tangential velocity, which is equal to 4 in the y direction. Therefore, you obtain 4j. The tangential acceleration at point A is also in the same direction. Therefore, you obtain 10j. So we want to measure the relative displacement B with respect to A. We can use this formula, RB/A equal to RB minus RA. For the derivation purpose, let's set the inertial frame as well as the rotating frame over here. What we are interested is, we want to find the displacement of B with respect to A in the inertial frame. It can be found by using the absolute displacement B that is observed in the inertial frame O, minus with the absolute displacement A that is observed in the inertial frame. Expand it, you obtain capital IJK, indicate the direction for the capital XYZ, and you have the magnitude XYZ for the particle B and particle A here. So XB minus XA give you XB/A, YB minus YA give you YB/A. Since the particle move in XY plane only, there is no movement in Z-axis. Therefore, the ZB/A is equal to 0. We have conveniently put the inertial frame capital XY to be the same direction with the rotating frame with small letter xy here. Since the direction for the capital I in the inertial frame is same with the small letter I in the non-inertial frame. Therefore, we can replace this by the small letter I here. And then we can replace this with the small letter j. This is because at this particular moment, they are in the same direction. So you success to obtain the displacement B relative to A in the inertial frame to be this answer. Next, we are going to find the relative velocity in the inertial frame by taking the derivative of RB/A. So substitute the relative displacement into this, you obtain this answer. And we know that VB/A is the relative velocity between VB minus VA. Let's continue with this component. So you have VB minus VA, which is equal to differentiate XB/A with respect to time and take the I to be constant, plus differentiate dI over dt and take the XB/A to be constant. Differentiate this term, you have dy over dt and take the j to be constant, plus dj over dt and take the y to be constant. Small letter I and j are the unit vector in the rotating frame, and they can change with respect to time. For example, at this particular moment, your I and j is over here, but over some time when the thing moves to here, then you have I, j in different directions. In this case, di over dt and dj over dt are no longer equal to 0, and we need to find out what is the answer for this. So this is the initial position for the ij direction. When the particle A moves to the next position here, you see the frame is rotate in clockwise. So the frame is rotate now from y to y prime, x to x prime. And the unit vector I and j are rotate to the I prime and j prime. And the angle between them are the d theta, and this angle is very small, is approximate to 0. Since the angle is very small, therefore the change in the I direction, which is your di, can be approximated to a linear line here, and we can use the arc length formula x equal to r theta to compute the di. So di here represents the arc length vector, which is the x. The magnitude of the arc length is equal to the radius multiplied with the theta. So in this case, the radius is equal to 1 because the magnitude of the unit vector is equal to 1. Therefore, you can multiply 1 inside. So this is your radius. And the angle theta is equal to d theta. So this is your magnitude. For the vector di, you need the magnitude as well as the direction. So your di is moving downward, which is the opposite direction to the j direction here. Therefore, we can put the direction to be negative j. With that, we success to obtain the di vector. We continue to find the dj vector here. So the arc length here is dj is equal to the radius. So radius for unit vector j is equal to 1 and the angle is d theta. Therefore, dj is equal to 1 multiplied with d theta. So this is the magnitude. The direction is in same direction with the x direction. Therefore, we need to multiply with the I direction. With that, you success to obtain the dj vector here. By taking the first equation and then differentiate it with respect to time on both sides, then you obtain di over dt on your left hand side, and on your right hand side, d theta divided by dt, you obtain the angular velocity. This is angular velocity for the frame rotation. Therefore, we use the ohm to represent the theta dot. By using the same approach to the second equation, divide dt on both sides, you obtain dj over dt, d theta divided by dt, you obtain theta dot, which can be equal to ohm. So this is the formula that we obtained so far for the change of I direction and j direction with respect to time. And you should know the theta dot here is equal to the ohm, which is the angular velocity for the rotating frame. We can convert these two formulas into the vector format. The velocity vector is equal to angular velocity crossed with the radius. By using the same concept, we obtain the velocity due to the change in the I direction is equal to the angular velocity in ohm crossed with the radius in terms of unit vector. Let's check if these two formulas are valid or not. So you have the rotation frame, which is rotate in the clockwise. Therefore, you have x, y, z axis, and since it's rotate in clockwise, the direction for the ohm vector will be in negative direction to the z axis, which is negative k. You can obtain this direction easily by using the right hand rule. Cross your finger, follow the rotation here, then you found your thumbnail pointing to the negative z direction. So this is the direction for your angular velocity. By applying the cross product here, take the ohm cross with I. So using the right hand rule, take the ohm cross with the I here. Then you should be able to obtain the direction of ohm cross I is pointing downward. Is in the same direction with the di over dt. Therefore, we can say that this equation is valid. By taking the ohm cross with j, so let's use the ohm cross with j here. By using the right hand rule, you should obtain ohm cross j to be this direction. So when you check, this direction is the same direction with dj over dt. Therefore, this equation is valid as well. If the angular velocity and angular acceleration are given for a rotating frame, and the direction of the rotation is given as well, then you must know what is the magnitude and direction for the ohm and ohm dot vector. Previously, we have success to use the right hand rule to determine the direction for angular velocity to be in negative k direction, which is here. If the angular velocity is positive, then your angular velocity will increase over time. then the dot vector will be in the same direction with the angular velocity. If the angular acceleration is given in negative value, then the angular velocity will decrease over the time. So in this case, the dot vector will be in the opposite direction to the movement, which is positive k, which is different with negative k here. So you must know how to decide the direction for and dot. If the rotating frame is rotated in the counterclockwise direction with respect to the z-axis, then in this case, your vector will be in positive k direction. If the dot is positive, then the dot vector will be in the positive k direction as well. If the dot is negative, then the dot vector will be in the opposite direction to So far we have determined the relative velocity Vv minus Va to be these four components, and we have success to obtain the di over dt and dz over dt to be these two vectors. By substituting di over dt inside this formula as well as the dj over dt, then you should get this answer, and we are going to discuss what is the meaning for this term and the second term here. For the first term, this is the change in terms of the relative displacement for the x and y axis with respect to time. So we know that this term is equal to Vv/a in the bracket small letter xy. This means the velocity of v relative to observer at a in the rotating xy frame. We can also call this as the relative velocity. For the second term, since xb/a is a constant as well as the yb/a, so you can multiply the constant inside to obtain these two terms. Collect the term for the cross here to outside, then you obtain this result. So this term is the relative displacement v with respect to a, therefore you can substitute it with this. In total, the differentiation of the rb/a with respect to dt in fixed axis xy here is equal to the first term plus the second term. It's very important that you understand the Vv/a in the bracket of small letter xy is measured by the rotating observer in A. You have additional term here which is due to the rotation of the frame. This velocity is not measured by the rotating observer at A here. It can be only measured by the observer in inertial frame. Previously, we want to find the velocity at point B, which is here, and we can find it by using the relative motion analysis, which is VA plus the relative velocity, which is the change of the relative displacement of point B with respect to time here, that is measured from A. Through the derivation, we success to obtain two terms from this component, and this equation is the most important velocity equation that is applicable to the 3D problem. It says that to find the absolute velocity of point B here, if you can't measure it directly from the left hand side, you can use the relative motion analysis on the right hand side to find the answer. So you have the VA, which is the absolute velocity of the A here. Then you have the relative velocity VB/A that is measured from the A here. If A is a rotating frame, then the relative velocity that you measure is in a small letter xy. Lastly, you need to consider the rotating effect of the frame. It's important that you know this velocity due to the rotating frame effect are measured by the observer A, which is in the rotating xy frame. This component must be measured in the inertial frame. This is because the observer A do not know how much angular velocity for the rotating frame, and this term must be measured with respect to inertial frame. In simple, bear in your mind, to find the absolute velocity Vb is equal to absolute velocity Va plus the relative velocity Vb/A in the bracket of xy to indicate the A observer is in rotating frame, and lastly you need to add the rotating effect. Let's solve the previous problem Find the relative velocity of B with respect to A by using this equation. So you want to find the velocity at B with respect to A. However, in this case, the A is the rotating frame. Therefore, you need to consider the rotating effect. Since the frame is rotating counterclockwise with respect to the z-axis, therefore the angular velocity of the frame must be in positive k direction. How about the magnitude of the angular velocity? In this case, the angular velocity of the rotating frame, which is O, is equal to the magnitude of the angular velocity for the object, which is omega. So to find the omega, since you know V tangent for the point A is equal to the R radius multiplied with the omega, so substitute V inside and radius inside, you can find your omega equal to 4 divided by 0.5. So this is the magnitude of the angular velocity. So in this case, the angular velocity of the rotating frame is equal to this. And to know either it's positive or negative, we check whether it's clockwise or anti-clockwise rotation. Initially, the frame is in this direction. Over the time, the frame moves to this point and is rotated in clockwise direction. Clockwise rotation with respect to your z-axis gives you negative k. So there's a correction here. This should be negative k. So based on the right hand rule, you should obtain negative k here. So the magnitude we have discussed earlier is equal to 4 divided by 0.5. Therefore, you should obtain negative 8k for your ohm. So you success to find the ohm to be this answer. Let's look at VB. So VB is over here, is moving to the left hand side. So left hand side is the negative I direction. Therefore, you obtain VB equal to negative 8 in I direction. Then you have VA. VA is over here, which is moving in the Y direction. Therefore, you have 4 in the J direction. So your VA is equal to 4J. Lastly, we need to compute this component. And ohm cross RB/A, you need to find the displacement of B with respect to A, which is over here. The distance between point A and point B is given by 0.8. Since this vector is moving in the negative J direction, therefore you obtain the RB/A is equal to the magnitude equal to 0.8 and the direction is negative J direction. With that, we obtain it to be negative 0.8 J. To compute this component, then you need to perform the cross product by using the determinant. So you have I, J, K. So for the first vector, you have 0, 0, negative 8K. Then you have 0, negative 0.8, A plus 0. Then you should have positive I, negative J, and positive K. So cross the first column, first row, then you obtain 0, negative 8, negative 0.8, and 0 for the determinant. Then cross the column for the J and row here, then you obtain 0, 0, negative 8, 0 for this determinant. Then cross the row and column for K here, then you obtain 0, 0, 0, negative 0.8, which is this component. So you perform the calculation, then you found that these two terms can be cancelled equal to 0, and this term gives you negative 6.4i. Another approach to compute this is by using the cyclic rule, IJK. So when you cross I cross J, you obtain K. J cross K, you obtain I. K cross I, you obtain J. Therefore, from here you know when you take J cross K, you obtain I. So cross product, if you reverse it, you take the K cross with J, which is in this case, then you obtain negative I. So since you obtain negative I here, Then take the negative 8 multiplied with negative 0.8, you obtain 6.4. So the final answer is negative 6.4i. You get the same answer. Since we want to find the relative velocity VB/A, so you need to rearrange the equation. Take the VA to left hand side, you obtain negative VA. Take the ohm cross RB/A to left hand side, you obtain the negative component. Then substitute the value that you obtain inside and perform the calculation here, you should obtain this result. This is the velocity of point B here that is observed by the observer in point A. In this case, the point A is moving with rotating frame. So if you calculate the velocity without consider the rotating effect, then the relative velocity will be calculated wrongly. So you must consider the rotating effect into the calculation. Please make sure you master this equation to find the velocity. This is very important. So this is the equation to find the velocity at point B by using the relative motion analysis. Let's differentiate it to obtain the acceleration equation. Differentiate the absolute velocity at point B and point A, you obtain the acceleration B and acceleration A directly. Differentiate the relative velocity with respect to time, you obtain this term. Differentiate the velocity due to the rotation frame effect, then differentiate the ohm, you obtain d ohm divided by dt, and the r remain. Then differentiate the r with respect to time and remain the ohm, you obtain these two terms. So this is the result after you differentiate the velocity due to the rotating frame effect. Previously, we successfully obtained this equation. When you take the differentiation of the relative displacement v with respect to A in the inertial frame, you will obtain the relative velocity measured in a rotating frame plus a rotating effect. By using the same approach, you can find the differentiation of the relative velocity by replace the RB/A here to be VB/A. And then replace the VB/A with the AB/A. Substitute these two equations inside, then you should obtain this answer. When you compare, you have the AB here, AA here. Differentiate ohm with respect to time, then you obtain the ohm dot, which is the angular acceleration. With that, you obtain this acceleration component. Ohm cross with the first term here, give you this acceleration. Ohm cross with the second term here, then you obtain ohm cross V. So you see, you also have ohm cross V component here. So when you take the summation, you obtain 2 ohm cross V. Lastly, you have AB/A acceleration. You need to be careful. In many books, this term is simplified to this, where we can compute the vector triple product here by using the BAC CAB identity. Let the first vector to be A, second vector to be B, and third vector to be C. Then you can compute this triple product to be B in the bracket of A dot C minus with C in the bracket of A dot B. So substitute the ABC vector inside, then you should obtain this. In this case, the ohm is in the negative K direction, and the displacement B with respect to A is in the negative J direction, which is here. When you check the angle between these two vectors, you found that they are 90-degree different. For 2D motion case, the angular velocity of the rotating frame will be always 90 degrees with the motion, such as the velocity, acceleration, and displacement. Since we know the angle between ohm and RB/A is 90 degrees, therefore ohm dot RB/A you will obtain 0. Based on the dot product definition, when your angle is 90 degree, you have the cos 90 degree equal to 0. Therefore, this product will be equal to 0. So you only have this remaining term here. Ohm dot ohm can be further simplified by using the dot product definition. Since the angle difference between these two vectors is equal to 0, cos 0 gives you 1, so you obtain the result to be magnitude ohm multiplied with magnitude ohm, you obtain ohm squared. So we can simplify the vector triple product here to be this term if the angle between the ohm and the R is equal to 90 degrees. Only that this component can be cancelled, become 0. However, for the 3D case, the ohm and the motion may not at 90 degree difference. So in this case, we cannot use the simplified formula here to solve the problem. It's highly recommend you to use this formula to find the acceleration, as this formula can be applied to 2D as well as 3D case. We have success to derive the most important acceleration equation that can be used to find the acceleration at point B. AB is equal to the absolute acceleration at point A plus additional 4 acceleration components. So these 4 acceleration components you have learned in the polar coordinate chapter. However, this is in vector format, and in the polar coordinate chapter we are using the scalar format to solve the problem. You have the tangential acceleration, normal or the centripetal acceleration, coriolis acceleration, and the sliding acceleration. To find the angular acceleration of the rotating frame, we can use this formula. First of all, the rotation of the rotating frame is in the clockwise direction, and we obtain the ohm vector, which is the angular velocity for the rotating frame, equal to negative 8k. Since the tangential speed is increased at 10 meters per second square, therefore the ohm dot will be in the same direction with angular velocity here, which is in the negative k direction. Since we know the acceleration is equal to radius multiplied with the angular acceleration, therefore we can find the ohm dot here equal to the tangential acceleration, which is equal to 10 meters per second square divided by the radius, which is equal to 0.5. So 10 divided by 0.5, you obtain negative 20k. So this is the answer for the angular acceleration. AB is equal to 5 in this direction. This direction is I direction. Therefore, your AB is equal to 5I. Acceleration at point A has two components. This is because the object A is moving in a circular motion. Therefore, you have the tangential acceleration, which is equal to 10 in the J direction, which is this. And you have a normal acceleration towards the center. So this normal acceleration is equal to V tangential square divided by radius. So substitute the tangential velocity, which is equal to 4. Inside the formula, you obtain 16. Then divide it with the 0.5. You should be able to obtain the normal acceleration to be 32 in the I direction. We have obtained the ohm dot previously is equal to negative 20k. RB/A is the displacement at point B here with respect to A. So this vector is equal to 0.8 in the negative J direction. So you have negative 0.8J. Take the cross product between the ohm dot with this, you should be able to obtain this answer. For this term, you have obtained the ohm vector to be negative 8k previously. So you need to perform the vector triple product here. Please be careful, you need to perform these two components first. Take the cross product between these two components, you should obtain negative 6.4i, and then you continue to take the cross product between these two components, then you should obtain this answer. Previously, we obtained the relative velocity of B with respect to A, which is this symbol. So this is the answer that we obtained previously. Substitute inside this formula, and then take the cross product, you should obtain this answer. So we want to find the relative acceleration of B with respect to A here is equal to AB, which is equal to 5I, minus with the remaining term here. So move this to the left hand side, you obtain negative here. So you continue minus with the AA minus with the tangential acceleration, which is equal to negative 16I here. Then continue minus with this. This is the normal acceleration, or what we call the centripetal acceleration, which is equal to 51.2 J. Lastly, minus with this term, which is the Coriolis acceleration, then you should obtain this result.